Yesterday, something happened 203 million kilometers away that nobody expected to witness. And I need you to understand something right now while most of the world was sleeping, while the news cycle churned through its usual noise, while social media buzzed about everything except this 8 spacecraft positioned across the solar system, recorded something that's forcing scientists to rethink how we interpret astronomical data. How is that even possible that we're just learning about this now? October 29th, 2025, 11:47 UTC, Perihelion. That's the moment. That's when 3I Atlas III, confirmed interstellar visitor in human history, made its closest approach to our Sun. And here's what makes this different from every other celestial event you've heard about. Mainstream sources told you it would be invisible. They said the timing was terrible. They said solar conjunction would blind us. They were partially wrong. Amateur astronomers caught it. Spacecraft tracked it. And the data coming back, data that's currently undergoing peer review, data that scientists are meticulously analyzing right now, shows characteristics that warrant serious continued study. Not sensational claims, not wild speculation, but legitimate scientific interest that goes beyond routine observation. Think about that for a moment. We're talking about an object travelling at 68 kilometers per second, that's 244,800 kilometers per hour, that originated from somewhere beyond our solar system, somewhere in the vast darkness between stars. And we just watched it whip around our Sun at the most critical observational window possible. The moment when solar heating reaches maximum intensity. The moment when, if this object were anything other than what it appears to be, we'd see definitive proof. What did 8 different viewing angles reveal? That's the question driving this entire investigation, because unlike Oumuamua, which we only detected after it had already passed perihelion, and was racing away from us unlike 2I/Borisov, which we tracked, but never had positioned so many instruments to observe simultaneously, 3I Atlas gave us something unprecedented. A comprehensive, multi-spacecraft observational campaign during the most important moment of its entire journey through our solar system. And while mainstream media focused elsewhere, while casual observers assumed there was nothing to see, a network of spacecraft spanning Mars' orbit to the inner solar system was recording data. Precise data, technical data, the kind of information that takes weeks to analyze properly because you can't rush science. You can't jump to conclusions, you follow the evidence wherever it leads. Here's what I can tell you right now, before we dive deep into the technical details, before we examine each piece of evidence, before we explore what this means. Preliminary observations, and I want to stress that word, preliminary, show that 3I Atlas exhibited characteristics during perihelion passage that are keeping scientists engaged in ongoing analysis. Not because the data is inexplicable, not because we've found alien technology, but because comprehensive spacecraft coverage during an interstellar object's perihelion has never happened before at this scale. We're watching analysis unfold in real time. We're seeing the scientific process work exactly as it should. Observation, data collection, peer review, publication. And somewhere in that process, between what was observed and what it means, lies a story that challenges us to think carefully about how we interpret the universe. You need to understand why I'm telling you this story now. Because by the time peer-reviewed papers hit major journals, by the time official NASA press releases get written, by the time the mainstream catches up, you'll have already seen the pattern emerge. You'll have already understood what made yesterday significant. You'll have already connected dots that most people don't even know exist yet. So if you want to understand what comprehensive spacecraft observations revealed during perihelion data that's undergoing peer review right now, data that represents the most thoroughly documented interstellar visitor perihelion in history, hit that like button. Drop a comment. Were you tracking 3I Atlas yesterday? What aspect of interstellar visitors fascinates you most? Because the scientific story emerging from October 29th challenges us to think carefully about how we interpret astronomical data. And I promise you, by the end of this analysis, you'll understand why timing matters, why spacecraft positioning matters, why perihelion is the acid test for understanding what we're really looking at, and why what happened yesterday might be the most comprehensively observed moment in the history of interstellar visitor studies. Let's start with why that moment mattered so much. You want to understand why scientists care so much about perihelion? Let me show you what happens when an object moving at interstellar velocities encounters the gravitational well and radiation intensity of a star. Perihelion isn't just the closest approach, is not simply a geometric point on an orbital path. Perihelion is a crucible. It's where physics reveals truth. It's where the difference between a comet and something else becomes undeniable if there's a difference to find. October 29, 2025, at 11:47 UTC, 3I Atlas reached its perihelion at 1.356 astronomical units from our Sun. That's roughly 203 million kilometers. For perspective, that's closer than Mars orbits at its nearest point, and at that distance, travelling at 68 kilometers per second. The object experienced solar radiation intensity of approximately 770 watts per square meter. Think about what that means. Every square meter of 3I Atlas was being bombarded with 770 watts of solar energy. That's not gentle sunlight. That's enough thermal stress to vaporize ice, to crack rock, to reveal anything hidden beneath the surface layer. It's enough energy to make a comet bloom into spectacular activity, or enough to test whether an artificial construct can maintain structural integrity under star proximity conditions. This is what astronomers call the acid test. If 3I Atlas was a typical comet, perihelion would trigger massive outgassing. Subsurface volatiles would vaporize. We'd see dramatic brightening, possibly several magnitudes. We'd see fragmentation events where thermal stress cracks the nucleus into pieces. We'd see the characteristic parabolic arc of dust and gas streaming away from the sun-facing side. Standard cometary behavior that we've documented hundreds of times. But here's what makes this perihelion different from every other interstellar visitor we've studied. The timing created a perfect storm of observational geometry. 8 days before perihelion, October 21st, 3I Atlas passed through solar conjunction as seen from Earth. That means from our perspective, the object was positioned almost directly behind the Sun. Only 12.8 degrees of elongation separated them. For ground-based telescopes on Earth, this geometry was challenging. Not impossible, but difficult. The Sun's glare dominates that region of sky. Most professional observatories wouldn't waste telescope time trying to image through solar glare. And that's what led to the mainstream narrative. Perihelion would be invisible. We'd miss the most critical moment. But here's what that narrative missed. Solar conjunction from Earth doesn't mean solar conjunction from Mars. It doesn't mean solar conjunction from spacecraft positioned throughout the inner solar system. And it certainly doesn't mean we couldn't observe it. It just meant Earth-based observation was compromised. Solar conjunction from Earth simultaneously positioned our spacecraft fleet optimally. Let me explain this geometry because it's crucial. When Earth, Sun and 3I Atlas aligned, creating that challenging 12.8 degree elongation from our perspective, spacecraft positioned at different orbital locations saw completely different viewing angles. Mars orbiters saw 3I Atlas against open space, not solar glare. Parker Solar Probe, positioned on the other side of the Sun, had an unobstructed view. SOHO and GOES 19, with their specialized coronagraphs designed specifically to block solar light and observe the corona, could track objects near the Sun that ground telescopes couldn't touch. And ESA's JUICE, the Jupiter Icy Moons Explorer, had achieved a 75-degree solar elongation. That's one of the best observational positions in the entire solar system. Direct view, no solar interference, optimal trajectory tracking. This is not luck. This is orbital mechanics. But the result was unprecedented. The most comprehensively observed interstellar object perihelion in human history. Compare this to what happened with Oumuamua. We didn't discover it until October 19th, 2017, but it had already passed perihelion on September 9th, more than a month earlier. We missed the crucible moment. We only saw Oumuamua tumbling away, already fading, already racing back toward interstellar space. Every observation we made was post-perihelion. We had to reconstruct what happened at closest approach through mathematical models and inference. With 2I/Borisov, we did better. We discovered it in August 2019, months before its December 8th perihelion. We tracked it. Hubble observed it. Dozens of professional observatories pointed instruments at it. But even 2I/Borisov didn't have the coordinated spacecraft coverage that 3I Atlas received. Most observations were Earth-based, single perspective, atmospheric distortion, weather interruptions. 3I Atlas changed that equation. For the first time, we had multiple spacecraft, positioned at different orbital locations, all capable of simultaneous observation during the most thermally stressful moment of an interstellar visitor's journey. Different viewing angles, different instrument types, spectroscopy from one platform, photometry from another, coronagraph imaging from a third, trajectory tracking from a fourth. This is what you need to understand about the Obert effect because it ties directly into why perihelion matters beyond just thermal stress. When an object moves through a gravitational field, its velocity at closest approach represents maximum kinetic energy. Any propulsive maneuver performed at perihelion gets amplified by the gravitational assist. Rocket scientists call this the Obert effect, and it's why spacecraft performing planetary flybys fire engines at closest approach, you get the most change in trajectory for the least fuel expenditure. If 3I Atlas were anything other than a natural object following ballistic trajectory, perihelion would be the logical moment to perform propulsive maneuvers, maximum efficiency, optimal energy return. The mathematics are unambiguous, and 8 spacecraft were watching to see if that happened. The solar heating also matters for another reason beyond outgassing. Artificial constructs would need thermal management. At 770 watts per square meter, anything with internal systems would need to radiate heat or risk overheating. That creates signatures, excess infrared emission, beyond what you'd expect from passive solar absorption, hotspots, temperature gradients that don't match natural thermal models. Perihelion reveals truth because physics doesn't lie. Natural comets respond to solar heating in predictable ways. The volatile ices sublimate water, carbon dioxide, carbon monoxide, methane. The gas drags dust with it, creating the classic coma and tail. Brightness increases follow power laws related to distance from the sun. We can model this. We understand the physics. Perihelion observations either match those models or they don't. That's the acid test. And what makes October 29th, 2025, historically significant isn't just that perihelion happened. It's that we were positioned to document it comprehensively. Multiple viewing angles eliminate ambiguity. If one spacecraft sees something unusual, maybe it's instrumental artifact. But if 8 different platforms with different instruments from different viewing positions all record consistent data, that's not artifact, that's reality. The geometry that made Earth-based observation difficult simultaneously made spacecraft observation optimal, and that's not a contradiction, it's orbital mechanics working exactly as mathematics predicts. So when you hear that perihelion was invisible, understand what that really means: challenging from Earth, optimal from spacecraft. And since spacecraft carry instruments that ground telescopes can't match specialized coronagraphs, plasma detectors, particle counters, instruments designed specifically for near-Sun observation, the data quality from yesterday potentially exceeds anything we could have captured from Earth anyway. This is why timing matters. This is why October 29th represents a watershed moment. Not because something sensational happened, we don't know that yet, but because regardless of what 3I Atlas is, we documented its most revealing moment better than any interstellar visitor before it. And now, with that context established, you need to understand who was watching and what they were capable of recording. Let me walk you through the fleet that had eyes on 3I Atlas during its perihelion passage. Because understanding who was watching matters as much as understanding what they saw. Start with Mars. On October 3rd, 2025, 26 days before perihelion, Mars was positioned at 0.19 astronomical units from 3I Atlas. That's approximately 28 million kilometers. In astronomical terms, that's practically next door. And orbiting Mars, we have an array of sophisticated spacecraft that most people don't think about. Perseverance rover with its Mastcam-Z camera system, capable of tracking celestial objects. MAVEN orbiter studying atmospheric escape. Mars Express with its high-resolution stereo camera, and the Trace Gas orbiter with spectroscopic capabilities. These aren't just Mars science platforms. They're space-based observatories with instruments that can be tasked for opportunity targets. And 3I Atlas, passing within 0.19 astronomical units, qualified as an opportunity target. What could Mars orbiters detect? Trajectory. If 3I Atlas deviated from gravitational prediction by even fractions of a degree, multiple observations from Mars' position would reveal it. Spectroscopy. Mars orbiters could analyze reflected sunlight, looking for emission lines indicating specific chemical composition. Photometry. Brightness measurements over time showing how the object responded to increasing solar heating. But Mars observation was early October 3rd, 26 days before the crucible. What Mars platforms provided was baseline data. pre-perihelion characterization against which perihelion observations could be compared. Now move inward to Parker Solar Probe. On October 2nd, 27 days before perihelion, Parker was positioned at 1.612 astronomical units, roughly 241 million kilometers from 3I Atlas. Parker's primary mission is studying the solar corona, diving repeatedly closer to the Sun than any spacecraft in history. But Parker carries WISPR, the Wide-Field Imager for solar probe designed to photograph the corona and solar wind. WISPR can also image any object in its field of view, and 3I Atlas entered WISPR's field of view. Parker Solar Probe observations matter because WISPR sees wavelengths and faint structures that ground telescopes miss. It's positioned to observe solar wind interaction, how charged particles from the Sun interact with any object passing through the inner solar system. If 3I Atlas had a magnetosphere, WISPR might detect it. If plasma dynamics around the object showed anomalies, Parker was positioned to record them. Then we have the coronagraph platforms, SOHO and GOES-19. These spacecraft exist specifically to block the Sun's overwhelming brightness and photograph the corona, the superheated outer atmosphere of the Sun visible during total solar eclipses. Coronagraphs use an occulting disk to create artificial eclipse conditions, allowing them to see objects near the Sun that would otherwise be lost in glare. SOHO. The Solar and Heliospheric Observatory has been watching the Sun continuously since 1995. Its LASCO coronagraph has accidentally discovered over 4,000 comets that pass too close to the Sun to be visible from ground telescopes. On October 18th through 24th, SOHO's field of view included 3I Atlas. During those critical days approaching perihelion, SOHO could track the object against solar background. And here's where amateur astronomer Waracheti Boonplod enters the story. On October 29th, perihelion day, Boonplod was reviewing SOHO imagery and spotted 3I Atlas at magnitude +11, just as predicted. He confirmed visibility despite solar conjunction. He documented standard coma and tail morphology. He proved that the invisible perihelion narrative was incorrect. That matters enormously, because it means we have visual confirmation from an independent observer, not NASA, not ESA, but a citizen scientist reviewing public data that 3I Atlas was observable during perihelion and displayed normal cometary features. GOES-19, the latest geostationary operational environmental satellite, carries the CCOR-1 coronagraph as part of its space weather monitoring mission. GOES-19 corroborated SOHO observations, providing redundant confirmation that 3I Atlas remained visible and traceable throughout perihelion passage. But the platform with perhaps the most optimal viewing geometry was ESA's JUICE Jupiter, Icy Moons Explorer. Launched in April 2023, JUICE is currently on its 8-year journey to Jupiter, where it will study Ganymede, Callisto and Europa. But during October 2025, JUICE's trajectory positioned it at 75° solar elongation, relative to 3I Atlas. That's optimal. That's the viewing angle astronomers dream about. No solar glare, direct view, unobstructed sightline. JUICE carries a suite of scientific instruments including Janus, optical camera, MAGIS, spectrometer, and UVS, ultraviolet spectrograph. While these instruments are primarily designed for Jupiter system studies, they're fully capable of observing other targets when opportunity allows. And 3I Atlas at perihelion definitely qualified as an opportunity. Then there's Europa Clipper, which launched in October 2024 and is now en route to Jupiter on a trajectory that brought it within observational range during the October window. Clipper carries thermal instruments, spectrometers, and cameras that could theoretically contribute data if mission planners allocated time for the observation. Solar Orbiter, ESA's mission to study the Sun from varying orbital distances, was also positioned to contribute observations. Its suite of instruments designed to study solar phenomena could characterize how solar wind and radiation interacted with 3I Atlas during close approach. Now let's talk about what each platform could detect, because capability matters as much as position. Spectroscopy tells us what something is made of. When sunlight reflects off an object, specific wavelengths get absorbed by molecules in the surface material or outgassing volatiles. Those absorption lines are like fingerprints. Carbon dioxide absorbs specific wavelengths, water ice absorbs others, organic compounds have distinct signatures. Multiple spacecraft carrying spectrometers could independently verify composition and look for unusual spectral features. Photometry measures brightness over time. As 3i Atlas approached perihelion, its brightness should have increased following predictable mathematical relationships. Any deviation from expected brightness curves would indicate unusual behavior, either more activity than predicted or less. Multiple platforms measuring brightness from different positions could detect whether the object reflected light uniformly or showed geometric effects suggesting non-spherical shape. Trajectory tracking requires multiple observations over time to calculate precise position and velocity. With spacecraft positioned at different orbital locations, triangulation becomes possible. Any deviation from purely gravitational trajectory, any thrust event, any course correction would show up as trajectory anomaly. The more observation points, the more precisely you can calculate whether the object is following natural ballistic path or under some form of control. Morphology, imaging, means photographing the object's shape and structure, coma size, tail orientation, nucleus brightness, dust distribution. Natural comets show specific patterns: dust fountains from the sun-facing side, anti-solar tail pointing directly away from the sun, coma size related to outgassing rate. Artificial objects wouldn't necessarily show these features, but here's what we expected to see based on pre-perihelion data, and this is crucial because expectation informs interpretation. Before perihelion, ground-based telescopes had been tracking 3i Atlas for months. Nordic Optical Telescope in the Canary Islands, Palomar Observatory in California, Apache Point Observatory in New Mexico. These aren't amateur setups. These are professional research facilities with sensitive instruments and experienced observers. Their observations from July through October 2025 had established baseline characteristics. Brightness had been increasing following a power law with exponent around n equals 3.8, consistent with a comet approaching the Sun. Spectroscopy had detected carbon dioxide and water ice signatures, exactly what you'd expect from a comet. Morphology showed evolution from a sun-facing dust fan to an anti-solar tail, as solar heating increased textbook cometry evolution. Based on this pre-perihelion data, scientists predicted that at perihelion, 3i Atlas should brighten to magnitude +11 to +11.5, bright enough to see with moderate amateur telescopes, if not for solar conjunction. Outgassing should increase, possibly dramatically. The tail should become more prominent. There might even be fragmentation events from thermal stress. Standard comet behavior, natural physics, predictable outcomes, and that's exactly what the spacecraft network was looking for, either confirmation of predicted behavior or deviations that would demand explanation. What I haven't told you yet, what you need to understand before we examine what was actually observed, is the context of what we knew going into that perihelion moment. Because science doesn't happen in a vacuum. We didn't enter October 29th blind. We had months of data, dozens of observations, published scientific papers characterizing this object, and some of what we knew was unusual even if naturally explicable. Before we talk about what spacecraft recorded during perihelion, you need to understand what made 3i Atlas interesting in the first place, because this wasn't just another routine interstellar visitor. Even before perihelion, even before October 29th, this object had characteristics that kept astronomers engaged. Let's start with composition. Spectroscopic observations through the summer and fall of 2025 confirmed that 3i Atlas was outgassing carbon dioxide and water ice. That's normal for comets, in fact. It's the defining characteristic of comets. As they approach the Sun and surface temperature increases, subsurface ices sublimate directly from solid to gas, creating the characteristic coma and tail. But the ratio of carbon dioxide to water was noteworthy. Most solar system comets show water as the dominant volatile with CO2 as secondary component. 3i Atlas showed stronger CO2 signatures relative to water than typical. Not unprecedented, we've seen CO2-dominated comets before, but unusual enough to warrant attention. It suggests formation in a colder stellar environment than our Sun, where CO2 could condense more readily than in our solar nebula's history. Then came the nickel emission detection. Nickel. Atomic nickel gas in the coma. If you're not an astronomy specialist, that might sound alarming. Nickel? Isn't that a metal? Why would a comet be outgassing metal? But here's the context. We've seen this before. Comet C/1996 B2, Hyakutake showed nickel emission. So did C/1995-01 Hale-Bopp. In 2021, a comprehensive study of solar system comets found that nickel and iron emission lines appeared in many comets, likely from metal-bearing minerals in the nucleus being vaporized by solar heating. It's unusual but documented. For 3I Atlas, the nickel emission suggested metal content in its nucleus composition. That's interesting because it tells us something about the protoplanetary disk where this object formed billions of years ago. It suggests that disk had sufficient metallicity to incorporate nickel-bearing minerals, which has implications for the age and composition of its parent stellar system. Strange? Yes. Inexplicable? Number. The antitail phenomenon was perhaps the most visually striking pre-perihelion observation. In late September and early October, observers reported seeing material that appeared to move sunward opposite the direction tails normally point. Antitails sound impossible. They violate the basic physics of how solar radiation pressure pushes dust away from the sun. But antitails are actually well understood projection effects. When Earth's orbital position relative to a comet creates certain geometric alignments, dust particles already in the antisolar tail can appear to point sunward due to perspective. It's the same reason why railroad tracks appear to converge toward the horizon. Perspective creates visual effects that don't reflect physical reality. The antitail didn't represent material moving toward the sun. It represented our viewing angle, creating an optical illusion. Spacecraft from different positions wouldn't see the same effect, which is exactly what we'd expect if it were purely geometric. Brightness evolution through pre-perihelion months followed a power law relationship. Brightness increased proportionally to heliocentric distance, raised to an exponent of 3.8 plus or minus 0.3. That means as 3I Atlas got closer to the Sun, it brightened predictably according to a mathematical formula that describes how sublimation increases with temperature. This is normal. This is what comets do. The exponent value of 3.8 is slightly steeper than typical comets, which usually show exponents around 3 to 4, but well within the range of observed natural comets. A steeper exponent just means activity increased more rapidly with solar heating, suggesting volatile-rich composition. Dust production rates also followed predictable patterns, varying as heliocentric distance to the power of 1.8 plus or minus 0.3. Again, this is standard cometary physics. More solar heating equals more gas production equals more dust dragged off the surface. The relationship isn't linear, it's exponential because sublimation rate depends on temperature, and temperature relates to solar radiation intensity, which follows inverse square law with distance. All the mathematics lined up. All the physics made sense. Morphology observations from the Nordic Optical Telescope and other facilities showed 3I Atlas evolving exactly as you'd expect a comet to evolve. Early observations in July and August showed a sun-facing dust fan material being pushed toward the sun by outgassing jets on the far side of the nucleus. As solar heating increased through September and October, that morphology transitioned to a more symmetric coma and well-defined antisolar tail. This is textbook cometary evolution. It's what happens when a comet transitions from distant low-activity state to perihelion, high-activity state. We've documented this progression hundreds of times with solar system comets. But and this is important, there was one characteristic that couldn't be easily dismissed: trajectory deviation, non-gravitational acceleration. That's the technical term for when an object's trajectory doesn't match pure gravitational prediction. When you calculate where an object should be based solely on the Sun's gravity and planetary gravitational perturbations, and then you observe where it actually is, sometimes there's a discrepancy. 3I Atlas showed non-gravitational acceleration. Before you jump to conclusions, understand that non-gravitational acceleration is normal for comets. It's called the rocket effect, and it's simple physics. When volatiles sublimate from the surface and gas jets shoot into space, they create thrust. If that outgassing is asymmetric, stronger on one side of the nucleus than the other, it pushes the comet slightly off course. We see this constantly in solar system comets. We saw it with 2I/Borisov. It's one of the confirming pieces of evidence that an object is actually a comet rather than an asteroid. Asteroids don't outgas, so they don't show non-gravitational acceleration. Comets do. The magnitude of acceleration for 3I Atlas was consistent with normal outgassing forces, not large enough to suggest propulsion, not showing the characteristics of controlled maneuvering, just the expected slight trajectory modification from asymmetric outgassing. But it's worth noting because when you combine normal explainable characteristics together, Pattern-seeking minds start seeing design where there's only coincidence. Let me list the 8 characteristics that taken together made 3i Atlas a topic of conversation beyond just normal astronomical interest. 1. Trajectory deviation from pure gravitational path explained by asymmetric outgassing. 2. Near-ecliptic orbital alignment at only 5 degrees inclination explained by observational bias in how we discover comets. 3. Specific interstellar velocity of 44 km per second explained by galactic population statistics for thick disk stars. 4. Solar conjunction timing that complicated Earth observation explained by orbital mechanics and geometry. 5. Unusual morphology in pre-perihelion observations explained by evolving dust production patterns. 6. Emission patterns including CO, 2 dominance and nickel, explained by formation conditions and documented precedents. 7. Brightness fluctuations following power law but with steep exponent explained by volatileric composition. 8. Planetary flyby sequence including Mars, Venus and eventual Jupiter approach, explained by hyperbolic trajectory geometry. Each individually explained, each with natural precedent, each fitting within understood physics. But together they create a pattern that feels, to some observers, like it might be more than coincidence. And that brings us to the critical question. What happened when this object with its 8 interesting but explicable characteristics underwent the crucible test of perihelion? What did the spacecraft network actually observe when 770 watts per square meter of solar radiation hit 3i Atlas, travelling at 68 km per second at 1.356 astronomical units on October 29th? This is where curiosity meets reality. This is where speculation confronts data. This is the section you've been waiting for. What did 8 spacecraft, positioned across the solar system, actually record during the most critical observational window in 3i Atlas's journey through our stellar neighbourhood? Let me start with what's been verified and what's still undergoing analysis, because that distinction matters enormously in an era where rumours spread faster than peer-reviewed papers. On October 29th, 2025, amateur astronomer Warachati Boonplod was reviewing publicly available SOHOLA SCOC 3 coronagraph imagery when he identified 3i Atlas at magnitude +11, almost exactly as predicted by perihelion brightness models. That observation alone is significant. It confirms the object remained visible despite solar conjunction and that brightness evolution matched natural cometary physics. Boonplod's images showed standard coma and tail morphology, the classic antisolar tail orientation pointing directly away from the Sun, just as radiation pressure physics demands. Coma size consistent with active outgassing at perihelion distance. No unusual structural features, no geometric anomalies, no characteristics that would make an experienced comet observer pause and think, that's not natural. GOES. 19C-COR-1 coronagraph data corroborated these observations. Multiple platforms, different instruments, same conclusion. 3. I-Atlas looked like a comet behaving exactly as comets behave. Pre-perihelion spectroscopy from ground observatories, the data that had been accumulating through summer and fall showed carbon dioxide and water ice sublimation, matching natural comet composition. The spectral signatures didn't change dramatically at perihelion. They intensified, as you'd expect from increased solar heating. But the chemical fingerprints remained consistent with volatile-rich cometary material. Nordic Optical Telescope morphology observations tracked the evolution from pre-perihelion dust fan to perihelion-enhanced tail. That progression followed documented cometary evolution patterns. No surprises, no discontinuities, just natural response to increasing solar radiation. Trajectory data, and this is crucial, showed that 3i Atlas maintained the predicted path consistent with gravitational dynamics, plus the expected outgassing forces. There were no sudden trajectory changes, no course corrections, no evidence of propulsive maneuvering that would indicate control. If perihelion was the acid test, the moment when artificial objects would need to perform Oberth effect maneuvers for maximum trajectory efficiency, 3i Atlas didn't do it. It followed natural ballistic trajectory, modified only by the rocket effect of asymmetric outgassing. The same physics that explains every other active comet. Thermal response at perihelion matched models. At 770 watts per square meter solar radiation, the the temperature of the surface would reach approximately 200,250 Kelvin, depending on albedo and thermal inertia. That's cold enough to keep water ice stable in shadowed regions, but hot enough to sublimate CO2 and drive active outgassing. Infrared observations didn't show excess heat that would indicate internal power sources or thermal management systems. So what's the controversy? If all the data shows normal comet behavior, why are we talking about this? Because there's a gap between what's been publicly released and what comprehensive analysis might reveal. Because peer review takes time. Because spacecraft data, especially from missions like JU-ICE and Europa Clipper that weren't primarily tasked for this observation, requires processing, calibration, and validation before publication. And in that information vacuum, speculation breeds. Let me address the rumours explicitly because you've probably heard them. Rhythmic plasma pulses detected around 3I Atlas during perihelion, unverified, no published data, no peer-reviewed confirmation. This claim originated on social media and has not been corroborated by any official source. Parker Solar Probe, which would be the platform most likely to detect unusual plasma dynamics, has not released any data suggesting anomalous plasma behaviour. Could there be plasma dynamics we don't fully understand? Of course, cometary plasma interactions are complex, but rhythmic pulses suggesting artificial generation? No evidence supports that claim. NASA held emergency sessions to analyse the data, misleading framing. After any major observational campaign, especially for rare events like interstellar visitor perihelion science teams, convene to review data. That's standard procedure, not emergency response. The James Webb Space Telescope holds science team meetings after observations. New Horizons held meetings after the Pluto flyby. It's how collaborative science works. Calling routine post-observation analysis, emergency sessions transforms normal scientific process into conspiracy fuel. There's a data embargo until officials can control the narrative. Fundamental misunderstanding of peer review. When scientists make observations, they don't immediately publish raw data. They analyse it. They check for instrumental artifacts. They run models. They write papers. They submit to journals. Reviewers evaluate the methodology. This process takes weeks to months. It's not embargo. It's quality control. It's how we ensure published science is reliable rather than rushing half-analysed data into the public sphere where misinterpretation runs wild. The timeline for 3I Atlas data release follows standard protocols. Preliminary findings typically appear 24 weeks after observations, peer-reviewed papers 48 weeks, comprehensive analysis by the time of the next major observational opportunity, which happens to be the Jupiter flyby in March 2026. That's not suppression. That's science. But here's where it gets interesting, and this is why continued scientific attention is warranted, even though perihelion data shows normal comet behaviour. This is the first time we've had comprehensive multi-spacecraft coverage of an interstellar visitor's perihelion. That dataset is inherently valuable, regardless of whether the object is unusual. We can compare trajectory precision across multiple platforms. We can correlate spectroscopy with photometry with morphology. We can test our models of cometary physics using an object that formed around a different star. And there might be subtle features in that data not necessarily indicating artificiality, but revealing details about interstellar comets that we've never had resolution to see before. For instance, detailed spectroscopy might reveal isotopic ratios that tell us about the age and composition of 3I Atlas's parent stellar system. Was it formed in our galaxy's thick disk around an old metal-poor star? Or did it originate in a younger stellar population? Morphology analysis might show substructures in the coma jets, fountain features, active regions that reveal rotation rate and nucleus shape. We couldn't resolve those details in Oumuamua because we discovered it too late. We got some for 2I/Borisov, but not at this multi-angle precision. Trajectory tracking from multiple spacecraft positions might constrain the mass and outgassing rates more precisely than ever before, improving our models of how comets respond to solar heating. This is the contradiction that's driving continued interest. The data shows normal comet behaviour, but the quality and completeness of that data is unprecedented. Scientists aren't studying 3I Atlas because it's anomalous. They're studying it because it's the best documented interstellar comet perihelion we've ever achieved. Does that mean there's nothing unusual? Not quite. It means that what's unusual is the observational campaign itself, not necessarily the object. But, and I want to be completely transparent here, There remains the possibility that deeper analysis might reveal subtleties not apparent in preliminary observations. That's why peer review exists. That's why we wait for comprehensive papers rather than jumping to conclusions from initial data. If there were definitive anomalies, trajectory changes inconsistent with natural forces, thermal signatures indicating power sources, structural features incompatible with cometary material, we'd expect scientists to approach publication cautiously, because extraordinary claims require extraordinary evidence. You don't rush a paper claiming an interstellar visitor might be artificial. You triple-check everything. So the fact that comprehensive papers haven't appeared yet doesn't tell us whether the data is routine or remarkable. It tells us the scientific process is working as designed. What I can tell you is this. Based on what's been publicly released, Boonplod's SOHO observations, pre-perihelion spectroscopy, trajectory data, thermal models, 3i Atlas behave like a comet, an interesting comet with unusual composition and favourable observational geometry, but a comet nonetheless. And if that disappoints you, if you were hoping for confirmation of the artificial origin, I understand. But consider this. Comprehensive documentation of a natural interstellar comet's perihelion is itself a scientific milestone. We're learning about objects that formed light years away, ejected from their stellar systems, wandering the galaxy for millions or billions of years. That's profound even without aliens. Now, having established what the data shows, we need to examine those 8 characteristics I mentioned earlier in much more detail, because each one has been cited as evidence of possible artificial origin, and each one deserves thorough scientific scrutiny. Section 5. The 8 characteristics revisited natural explanations. You want to understand why some scientists see patterns where others see coincidence. Let me walk you through each of the 8 characteristics that make 3i Atlas interesting, showing you both why they sparked attention and why natural explanations exist for every single one. Let's start with trajectory deviation, the non-gravitational acceleration that some interpret as evidence of maneuvering. When you track an object's position over weeks and months, you can calculate extremely precise orbital parameters. You know where it should be based on gravitational forces alone, and when you observe where it actually is, sometimes there's a discrepancy. For 3i Atlas, that discrepancy exists. But here's what matters: the magnitude and character of that deviation. 3i Atlas shows acceleration consistent with the rocket effect from asymmetric outgassing gas jets, on one side of the nucleus creating thrust. We see this in virtually every active comet. It's not evidence of propulsion, it's evidence that the object is vaporizing material as it approaches the Sun. 2I/Borisov showed nearly identical non-gravitational acceleration. Comet 67P/Churyumov, Gerasimenko, visited up close by the Rosetta spacecraft, showed dramatic non-gravitational acceleration when outgassing was active. Halley's comet has had its orbit modified by outgassing for centuries. The acceleration vector for 3i Atlas points in the direction consistent with solar heating, creating stronger outgassing on the sun-facing hemisphere. It doesn't show the characteristics of controlled maneuvering, no sudden changes, no course corrections timed to orbital positions, no burns at perihelion where Oberth efficiency would be maximized. Natural explanation: asymmetric outgassing. Precedent: every active comet ever studied in detail. Second characteristic: ecliptic alignment. 3i Atlas's orbit is inclined only 5 degrees to the ecliptic plane, the plane where Earth and most planets orbit. Some find that suspicious. If objects approach from random directions in interstellar space, why would this one arrive so aligned with our solar system's primary plane? The answer is observational bias. Our best sky surveys, Pan-STARRS, ATL-AS. Catalina Sky Survey focus on the ecliptic because that's where near-Earth asteroids and potentially hazardous objects concentrate. We survey that region of sky more frequently and more thoroughly than high-inclination regions. If an interstellar visitor arrives at 60-degree inclination, it spends less time in the heavily surveyed ecliptic zone. We're statistically more likely to miss it. But an object arriving near the ecliptic plane stays within survey coverage longer and gets detected more readily. It's like looking for lost keys under the streetlight. You find them there more often not because keys preferentially fall near lights, but because that's where you're looking. Natural explanation: detection bias. We find what we search for most thoroughly. Third, velocity. 3. Atlas is travelling at 44 km per second relative to the local standard of rest, the average velocity of stars near the Sun. That's faster than typical solar neighbourhood stars, but not extremely so. Galactic population statistics show that stars in the thick disk, an older population dating from the galaxy's cosmic noon era, 913 billion years ago, have higher random velocities than younger thin disk stars. That's because they've been gravitationally stirred by spiral arm passages and molecular cloud encounters over billions of years. An object ejected from a thick disk stellar system would naturally have velocity around 4,050 km per second. That matches 3I Atlas perfectly. It's not evidence of artificial acceleration, it's evidence of old age and turbulent galactic history. Compared to Oumuamua, which had velocity around 26 km per second, more typical of thin disk population. Compared to 2I/Beresov at around 32 km per second intermediate population. The distribution matches exactly what you'd expect from random sampling of galactic stellar populations. Natural explanation: thick disk galactic origin. Precedent: stellar kinematic studies. Fourth, solar conjunction timing. The fact that perihelion occurred just 8 days after solar conjunction from Earth's perspective struck some observers as suspiciously timed, as if designed to hide the critical moment from ground observation. But orbital mechanics doesn't work that way. The date of perihelion is determined by the object's trajectory, velocity, and gravitational physics. It happens when mathematics says it happens. Solar conjunction timing is pure geometry, where Earth happened to be in its orbit when 3I Atlas arrived at perihelion. And as I explained earlier, that conjunction timing actually positioned spacecraft optimally. If there were an intelligence trying to hide perihelion, creating geometry that compromised Earth observation while optimizing spacecraft observation would be counterproductive. Natural explanation: orbital mechanics and geometric coincidence. Fifth, unusual morphology. Pre-perihelion observations showed morphological features that evolved over time: fans, anti-tail effects, asymmetric coma. Some interpreted these as non-natural structure. But cometary morphology is inherently complex and variable. It depends on rotation rate, active region distribution, dust grain size distribution, gas production rate, and viewing geometry. Every comet looks different because every nucleus has different topography and composition. The morphology evolution of 3I Atlas from sun-facing fan to symmetric coma to well-defined anti-solar tail follows the standard progression documented in cometary science textbooks. As solar heating increases, volatile activity increases, dust production increases, and morphology evolves accordingly. Nothing about 3I Atlas's appearance was incompatible with natural cometary structure. Natural explanation: complex but understood cometary physics. Precedent: every well-observed comet shows morphology evolution. Sixth, emission patterns. The CO2-dominated outgassing and nickel emission raised eyebrows. Shouldn't comets be water-dominated? Shouldn't metal emission be rare? Cometary composition varies enormously depending on formation conditions. Objects forming in the outer regions of protoplanetary disks, where temperatures never exceeded about 50 Kelvin, can retain CO2 and CO more readily than warmer regions where these volatiles don't condense. 3I Atlas likely formed beyond the CO2 snowline in its parent system, giving it composition different from inner solar system comets, but perfectly natural for outer system formation. Nickel emission, while unusual, has precedent. The 2021 study by Jean Monfroy and colleagues found iron and nickel emission in many comets, attributed to metal-bearing minerals being vaporized. It's rare but documented. And for an interstellar visitor, potentially formed in a system with different metallicity than our Sun, metal content might differ from solar system comets. Natural explanation: formation in cold, outer regions of a protoplanetary disk, possibly around a metal-rich star. Precedent: C/1996 B2, Hyakutake and other comets showing metal emission. Seventh, brightness fluctuations. The power law exponent of 3.8 for brightness evolution is steeper than typical comets, suggesting activity increased more rapidly with solar heating than average. But steeper than average doesn't mean unnatural. It means volatile rich. If 3I Atlas has abundant surface volatiles or low thermal inertia, it would respond more dramatically to solar heating. We see steep exponents in some solar system comets. It correlates with composition and structure. The fact that brightness followed a power law at all is evidence of natural physics. Artificial objects wouldn't necessarily follow predictable brightness relationships tied to heliocentric distance. Natural explanation: volatile rich composition with low thermal inertia. Precedent: observed range of cometary brightness exponents includes values above 3.5. Eighth, planetary flyby sequence. 3I Atlas passed Mars, Venus, and will eventually pass Jupiter. Some see that as a tour suggesting reconnaissance, but hyperbolic trajectory geometry determines flyby sequence. An object entering the inner solar system on a specific trajectory will pass whatever planets happen to lie along that trajectory. It's not choice, it's geometry. Thousands of comets have passed multiple planets. Every long-period comet from the Oort cloud makes a similar journey inward, past gas giants, past terrestrial planets, around the Sun, and back outward. The sequence depends entirely on trajectory inclination, perihelion distance, and timing. 3I Atlas's Mars flyby at 0.19 astronomical units was geometry. Venus flyby coming up is geometry. Jupiter flyby in March 2026 is geometry. It's following the path that mathematics dictates, not a planned reconnaissance route. Natural explanation: hyperbolic trajectory geometry. Precedent: every comet that passes through the inner solar system. 8 characteristics, 8 natural explanations, each with precedent, each with physics that works. Now here's where intellectual honesty requires me to say something important. The existence of natural explanations doesn't definitively prove natural origin. It proves that natural origin is sufficient to explain observations without invoking more complex hypotheses. This is Occam's razor, the principle that among competing hypotheses, the one requiring fewest assumptions is most likely correct. 3I Atlas can be explained entirely by natural cometary physics and galactic population statistics. That explanation requires only well-understood physics, no new assumptions, no exotic technology, no improbable coincidences. An artificial explanation requires assuming 1. Technological civilization exists, 2. They build interstellar probes, 3. They sent one here, 4. It's disguised as a comet, 5. All its behavior mimics natural physics perfectly, 6. It conducted reconnaissance but left no definitive evidence. That's a lot of assumptions compared to, it's a comet. But, and this is critical, there's one voice in the scientific community that disagrees with the natural consensus. One prominent astrophysicist who looks at these 8 characteristics and sees not just coincidence but possible pattern. And his credentials demand that we take his hypothesis seriously, even if most scientists disagree. Avi Loeb is not a fringe conspiracy theorist. He's not an amateur speculator with a YouTube channel. He's the former chair of Harvard's astronomy department, founding director of Harvard's Black Hole Initiative, former director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics. He's published over 1,000 scientific papers, advised dozens of PhD students, and received numerous awards for contributions to astrophysics. When someone with those credentials proposes that interstellar visitors might be artificial, you can't dismiss it as crackpot theory. You have to engage with the argument on its merits. Loeb's position on 3I Atlas and on Oumuamua before it rests on what he calls the acid test principle. Perihelion, in his view, is the definitive moment when natural comets should fragment or brighten dramatically from thermal stress. If an object survives perihelion without fragmentation and without dramatic outgassing increase, that's potentially significant. His argument goes like this: natural comets are fragile. They're loosely consolidated ice and dust held together by weak gravity, and possibly organic tars. When subjected to intense solar heating, 770 watts per square meter, at 1.356 astronomical units, thermal stress should crack them. We've seen comets fragment at perihelion dozens of times. It's expected behavior. If 3I Atlas passed through perihelion without fragmentation, that could indicate structural strength inconsistent with natural cometary material. It could suggest artificial construction engineered materials capable of withstanding thermal stress. Moreover, if outgassing was present but relatively modest enough to mimic natural comet behavior, but not as intense as some natural comets show, that could indicate controlled release designed to maintain the disguise. Loeb points to the 8 characteristics as potentially significant in aggregate. Yes, each has natural explanation, but together the pattern warrants consideration that we might be looking at something designed to appear natural, He estimates probability around 3040% that 3i Atlas might be artificial, not certainty, not even more likely than not, but significant enough that we shouldn't dismiss the hypothesis without thorough investigation. His methodology draws from SETI principles the search for extraterrestrial intelligence. SETI scientists analyze radio signals looking for patterns that natural astrophysical processes can't easily explain. Narrow bandwidth, frequency drift compensating for Doppler shift, modulation patterns suggesting information content. When you find those patterns, you take seriously the hypothesis that the signal might be artificial, even though natural explanations theoretically exist. Loeb applies the same logic to interstellar visitors. If an object shows characteristics that, while individually explicable naturally, together form a pattern consistent with artificial origin, we should investigate rather than assume natural origin by default. He founded the Galileo project specifically to conduct systematic scientific investigation of unidentified aerial phenomena and interstellar visitors using the rigorous methodology of mainstream astronomy, not to prove alien technology exists, but to check whether it does using the same observational and analytical tools we'd apply to any astrophysical question. Regarding perihelion observations, Loeb argues that what spacecraft should have seen if 3i Atlas were artificial includes controlled maneuvering using the Obert effect for trajectory adjustment, possible deployment of subprobes for reconnaissance, artificial lighting or heat signatures indicating internal systems, excess infrared emission from propulsion, or geometric emission patterns inconsistent with natural outgassing. If none of those were observed, that would argue against artificial origin. But here's his key point. We don't yet have comprehensive published data from all spacecraft platforms. Parker Solar Probe data hasn't been fully released. JUICE observations haven't been published. Europa Clipper potential data hasn't appeared in literature. Until comprehensive peer-reviewed analysis appears, Loeb argues, we should remain open to the possibility that subtle features in the full dataset might reveal something unexpected. He's also careful to distinguish his position from conspiracy thinking. He's not claiming NASA is hiding evidence. He's not suggesting government cover-up. He's saying that science moves slowly, peer review takes time, and provisional conclusions based on preliminary data might shift when comprehensive analysis is complete. The scientific community's response to Loeb's hypothesis is mixed but mostly skeptical. Most astrophysicists apply Occam's razor and conclude that natural explanation is sufficient until evidence demands otherwise. They argue that extraordinary claims require extraordinary evidence, and nothing about 3i Atlas exceeds the threshold of requiring artificial explanation. Dr. Matthew Knight of the US Naval Research Laboratory, who extensively studied 2I/Borisov, has stated that interstellar comets should look exactly like 3. The Atlas appears to look icy, outgassing, following natural physics. The fact that observations match natural predictions is evidence for natural origin, not against it. Dr. Michelle Bannister of the University of Canterbury, who studies trans-Neptunian objects and interstellar visitors, emphasizes that we're still in the early stages of understanding interstellar object population statistics. We've only confirmed 3, Oumuamua, 2I Borisov, 3I Atlas. Drawing conclusions about what's typical or unusual from a sample size of 3 is premature. Other scientists note that Oumuamua's unusual characteristics, extreme elongation, lack of visible coma, non-gravitational acceleration without detectable outgassing, were far more anomalous than anything 3I Atlas has shown. If we didn't conclude Oumuamua was artificial despite its strangeness, the bar for 3I Atlas is even higher. There's also methodological critique of assigning probabilities like 3040% chance of artificial origin. How do you calculate such probability without knowing how common artificial interstellar probes are, what they'd look like, or how they'd behave? The probability assessment, critics argue, is subjective rather than derived from statistical framework. But to Loeb's credit, he's not claiming certainty. He's claiming that the question deserves rigorous investigation, using best available instruments and methods. He's advocating for careful analysis rather than premature dismissal, and that's scientifically reasonable. The debate fundamentally comes down to burden of proof and prior probability. Most scientists start with low prior probability that any given interstellar visitor is artificial, so they require strong evidence to update that probability upward. Loeb argues that we shouldn't start with such strong priors, that we should let evidence speak more directly. It's a legitimate philosophical difference in how you approach anomaly hunting in astronomy. Neither position is unscientific, they represent different risk tolerances for false positives versus false negatives in detecting possible technosignatures. What both sides agree on, more data helps. Continued observations through upcoming flybys, publication of comprehensive peer-reviewed analysis, improved detection and tracking of future interstellar visitors for comparison. And that brings us to what's next, because the 3i Atlas story isn't over. Perihelion was one chapter. Additional observational opportunities are coming, and they'll provide more data to refine our understanding of what this object is. Perihelion is past. October 29th is behind us. But the scientific story of 3i Atlas continues, with 3 more critical observation windows that could add crucial data to our understanding. Let's start with Venus. On November the 3rd, 2025, just 5 days after Perihelion, 3i Atlas passes within 0.65 astronomical units of Venus. That's approximately 97 million kilometers. While there are no operational orbiters around Venus currently capable of detailed observation, Venus Express ended its mission in 2014, and Akatsuki's instruments are focused on atmospheric studies. Ground-based telescopes will have improved viewing geometry. By early November, solar elongation increases enough that Earth-based observation becomes more favourable. The object is moving away from solar conjunction, emerging into darker sky. Amateur astronomers with 10-inch or larger telescopes should be able to track it. Professional observatories can dedicate time without fighting solar glare. The Venus flyby offers spectroscopic opportunities, watching how the object's brightness and spectral signatures evolve post-perihelion. If thermal stress at perihelion damaged the nucleus or exposed fresh subsurface material, spectroscopy in early November might reveal compositional changes. Then comes December 19th, 2025 Earth closest approach at 1.80 astronomical units, approximately 270 million kilometers. That might sound distant, but it's close enough for detailed observation with ground-based instruments. Let me be crystal clear about something, because misinformation spreads fast. 1.80 AU presents zero threat to Earth. That's 270 million kilometers, roughly 700 times the distance to the Moon. There is no collision risk. There is no planetary defense concern. 3i Atlas will pass harmlessly, as its trajectory has always predicted. But December 19th represents optimal ground-based observation timing for another reason. By mid-December, 3i Atlas will be moving through the constellations Virgo and Leo, well away from the Sun in Earth's sky. Dark sky. Minimal solar interference. Professional observatories worldwide can coordinate observations. Spectroscopy can determine if outgassing continues post-perihelion or diminishes as the object moves outward and cools. Photometry can track brightness decrease and compare it to pre-perihelion approach phase. Morphology imaging can look for tail evolution, possible fragmentation debris, or structural changes. Amateur astronomer participation becomes crucial here. Distributed observation networks, dozens of amateur telescopes coordinating to provide continuous coverage, can track 3i Atlas through December and January as it fades. That crowdsourced data complements professional observations and fills gaps when weather or scheduling constraints limit access to large telescopes. You, watching this video, could theoretically contribute to 3i Atlas science if you have access to appropriate equipment and know-how. That's the beautiful democracy of modern astronomy. Important data doesn't only come from professionals. Then there's the IAWN listing, which has generated unnecessary alarm. The International Asteroid Warning Network listed 3i Atlas in its database, which some misinterpreted as emergency threat designation. Let me explain what IAWN actually is. It's a global collaboration coordinating asteroid detection, tracking and threat assessment. It catalogues objects that come reasonably close to Earth to ensure we have comprehensive trajectory knowledge. That includes asteroids, comets, and yes, interstellar visitors that pass through the inner solar system. 3i Atlas was listed because it's a comet passing within a few astronomical units of Earth. Comets get listed because outgassing jets can create unpredictable trajectory changes. That's the non-gravitational acceleration I discussed earlier. IAWN wants to track those changes to ensure predictions remain accurate. It's routine procedure. It's not threat assessment. It's standard cataloguing of objects that merit continued observation. Similarly, the astrometry training exercise scheduled from November 27, 2025 through January 27, 2026 uses 3i Atlas as a convenient target. Astrometry precision measurement of object positions requires practice and calibration. Using a real moving target that's being tracked by multiple observers provides excellent training opportunity. Space agencies regularly conduct these exercises. Using 3i Atlas doesn't imply anything suspicious. It implies that it's a well-tracked object at convenient distance and brightness for training purposes. The biggest observational opportunity comes in March 2026, Jupiter flyby. On March 16th, 3i Atlas passes within 36 astronomical units of Jupiter, about 54 million kilometers. That's close. That's within range of serious scientific observation. Europa Clipper, depending on its position in the Jupiter system at that time, might be able to conduct spectroscopic analysis. Jupiter's powerful gravitational field will also provide a natural test of 3i Atlas's trajectory. Any deviation from predicted gravitational dynamics would be unmistakable at that proximity. There's even a possibility, though uncertain pending mission planning, that Europa Clipper could sample material from 3i Atlas's tail if geometry aligns favourably. Cometary tails extend millions of kilometres. If Clipper's trajectory crosses the tail during March flyby, instruments designed to study Europa's ice plumes could instead analyse interstellar cometary material. That would be extraordinary. Direct sampling of material that formed around another star, brought into our solar system by 3i Atlas, analysed by sophisticated spacecraft instruments. The compositional data could reveal isotopic ratios, organic chemistry, and formation conditions from a stellar system light years away. The Jupiter flyby also provides gravitational interaction that tests trajectory models. If 3i Atlas follows precisely predicted path through Jupiter's gravity field, that's strong evidence for purely natural trajectory. Any anomaly, any deviation that can't be explained by Jupiter's gravity, plus continued outgassing, would demand explanation. After Jupiter, 3i Atlas continues outward, gradually fading as it retreats from the Sun and heads back into interstellar space. By mid-2026, it will likely be too faint for most ground-based observation. By 2027, only the largest telescopes could track it. Eventually, it vanishes back into the cosmic dark from which it came, another interstellar visitor that passed through our stellar neighbourhood and moved on. But the data remains. The observations persist, the papers get published, and our understanding of interstellar visitors improves incrementally, one object at a time. The timeline for comprehensive publications follows standard scientific procedure. Preliminary findings typically appear 24 weeks, post-observation in astronomers' telegrams or quick turnaround journals. Peer-reviewed papers describing detailed analysis take 48 weeks minimum. Comprehensive multi-author studies synthesizing data from multiple instruments and platforms can take months. For 3i Atlas, expect preliminary papers by late November or early December 2025. Major comprehensive studies by February or March 2026, likely timed to incorporate December Earth flyby data and positioned for March Jupiter flyby observations. Those papers will appear in journals like Nature, Science, the Astrophysical Journal, Icarus, or Astronomy and Astrophysics. They'll undergo peer review. They'll include data tables, spectroscopic plots, trajectory analysis, and detailed methodology. And they'll represent definitive scientific assessment based on best available evidence. Until then, we're in the information gap, that frustrating period where observations have been made, but comprehensive analysis isn't complete. And in that gap, speculation thrives. Which brings me to something important. How do you know what to believe in this information environment? Let me pull back the curtain on how science actually works, because understanding the process helps you evaluate claims about 3i Atlas, about any scientific topic, and distinguish legitimate findings from speculation. Science moves slowly on purpose. That's not bureaucracy. That's quality control. When a spacecraft makes observations or a telescope collects data, that's just the beginning. The raw data isn't immediately interpretable. It requires calibration accounting for instrumental quirks, noise sources, known systematic effects. It requires processing, extracting meaningful signal from background, calculating error bars, running statistical tests. Then comes analysis, comparing observations to theoretical models, testing hypotheses, ruling out alternative explanations. That takes time. For complex astronomical data involving multiple instruments and platforms, it can take weeks. Then comes writing, drafting a paper that explains methodology, presents results, discusses implications. That draft goes to co-authors for review and revision. Multiple rounds of internal critique improve clarity and catch errors. Then submission to a peer-reviewed journal. Editors send the paper to external experts, usually 3 reviewers who are scientists working in related fields. Those reviewers scrutinize methodology, check calculations, look for flaws in reasoning. They write detailed critiques. Authors receive those reviews and must address every criticism, either revising the paper to fix identified problems or explaining why the criticism doesn't apply. Revised paper goes back to reviewers. Sometimes multiple rounds of review occur before publication. This process takes 612 weeks minimum for fast-track publications in high-impact journals. For typical papers, 36 months is standard. Why so slow? Because rushing leads to errors. History of science is littered with premature announcements that didn't survive scrutiny. Cold fusion in 1989, faster-than-light neutrinos in 2011, phosphine in Venus's atmosphere in 2020. Each seemed revolutionary initially, but collapsed under closer examination. Peer review isn't perfect, it misses things sometimes, but it's vastly better than no review. It's the difference between Wikipedia, crowdsourced, variable quality, and Encyclopaedia Britannica, expert-reviewed, reliable. For 3i Atlas, the timeline is actually quite reasonable. Perihelion was October 29th. Preliminary observations appeared within days, Boonplod's SOHO analysis on October 29th itself, pre-perihelion spectroscopy from Nordic Optical Telescope published in October. That's fast, appropriate for time-sensitive observations. Comprehensive multi-instrument analysis will take longer because it's combining data from multiple spacecraft, cross-correlating observations, running complex models. That's the February-March 2026 timeframe. Compare that to other major astronomy milestones. When New Horizons flew past Pluto in July 2015, initial papers appeared in October 2015, 3 months later. Comprehensive studies continued appearing through 2016 and 2017. Rosetta's comet data, collected from 2014 to 2016, is still generating papers in 2025 as scientists extract new insights. Oumuamua was discovered October 19, 2017. First major paper appeared in Nature on November 20, 2017, 1 month later. But that paper was preliminary characterization. The controversial paper by Loeb and colleagues suggesting possible artificial origin appeared in November 2018, over a year later after extensive debate. So 3i Atlas, following a similar timeline, preliminary by late November, comprehensive by February-March, is completely normal. The emergency sessions narrative misunderstands how collaborative science works. After any major observational campaign, science teams convene, they hold video conferences, they share preliminary data, they discuss findings, they plan follow-up observations. That's not emergency response, it's standard collaboration. Calling those meetings emergency sessions transforms routine into conspiracy. It's like calling a business quarterly review an emergency board meeting, because executives are discussing important results. The data embargo narrative misunderstands peer review. Data isn't embargoed, it's being analysed. Scientists don't publish raw data immediately because raw data without context and interpretation isn't useful. Imagine releasing 50 gigabytes of spacecraft telemetry without explanatory paper who could interpret it except other experts in that specific instrument. Peer-reviewed publication is how science ensures quality. And yes, that creates a gap between observation and public understanding. But the alternative rushing preliminary interpretations into public sphere creates more confusion than clarity. Social media fills that gap with speculation. Someone sees a SOHO image and makes a claim. Someone else amplifies it. Within hours, NASA detected plasma pulses becomes accepted narrative, even though no such detection has been verified. Rumour propagates faster than correction. How do you evaluate claims in this environment? Here's a framework. Check sources. Is the claim from peer-reviewed paper or social media post? From professional astronomer or anonymous account? From official NASA press release or third-hand rumour? Verify through multiple channels. If something significant happened, multiple independent sources would report it. One source might be mistaken. 10 independent sources are more reliable. Wait for peer review. Preliminary findings might not survive detailed scrutiny. Peer-reviewed papers have passed expert evaluation. Distinguish preliminary from conclusive. Initial observations suggest is different from we have confirmed. Tentative findings deserve tentative confidence. Check your own biases. Are you more inclined to believe sensational claims because they're exciting, or dismiss them because they seem implausible? Neither extreme serves truth. Value the process. Science saying we don't know yet is honest answer, not evasion. Not knowing yet is vastly better than claiming to know based on insufficient evidence. Question everything, but follow evidence. Healthy skepticism applies to official narratives and alternative narratives equally. Demand evidence from all sources. Avoid false binaries. It's not believer versus skeptic or NASA versus truthers. It's evidence-based conclusions versus speculation. You can believe extraordinary things are possible while requiring extraordinary evidence before accepting they're actual. This framework helps you navigate not just 3i Atlas, but any scientific controversy. Vaccine effectiveness, climate change, quantum computing breakthroughs, archaeological discoveries. Process matters more than specific conclusions because process is how we converge on truth. For 3i Atlas specifically, here's what we actually know right now, today, as you're watching this. We know perihelion occurred October 29, 2025, at 1.356 astronomical units. That's verified. We know multiple spacecraft had favourable viewing geometry. That's geometry, not speculation. We know preliminary observations show normal cometary behaviour magnitude plus 11, standard morphology, anti-solar tail. That's from Boonplod's SOHO analysis, publicly verifiable. We know pre-perihelion spectroscopy detected carbon dioxide and water ice. That's from Nordic Optical Telescope and other facilities, published data. We know trajectory shows non-gravitational acceleration consistent with outgassing. That's from trajectory modelling documented in pre-perihelion papers. What we don't know yet, comprehensive spacecraft data analysis, detailed perihelion spectroscopy, long-term trajectory tracking post-perihelion, whether any subtle features in comprehensive dataset reveal unexpected characteristics. Not knowing yet is acceptable. It's honest. It's where we actually are in the timeline of scientific investigation. And that brings us to the question you've been waiting for me to answer directly. What do I think happened at perihelion? Let me synthesize everything we've covered and give you my assessment based on available evidence, not what I want to be true, not what would make the best story, but what the data actually supports. 3i Atlas behaved like a comet during perihelion. Brightness matched predictions. Spectroscopy showed natural volatile composition. Morphology displayed standard cometary features. Trajectory followed gravitational path modified by asymmetric outgassing. Thermal response aligned with models. No fragmentation events indicating structural weakness or unusual strength. Multi-spacecraft observations provided unprecedented quality data, enabling comprehensive analysis impossible with previous interstellar visitors. That dataset will advance our understanding of cometary physics and interstellar object population statistics significantly. If you wanted confirmation of alien technology, perihelion data, as currently understood from publicly released information, disappoints. Nothing in the observations demands artificial explanation. Everything fits within natural comet framework. If you wanted comprehensive scientific data on an interstellar visitor, perihelion data succeed spectacularly. We have multi-angle observations, varied instrument types, pre- and post-perihelion coverage, and trajectory tracking that will keep improving through 2026 flybys. The 8 characteristics that sparked initial interest all have natural explanations supported by precedent. Trajectory deviation, outgassing rocket effect, ecliptic alignment observational bias, velocity thick disk galactic population, solar conjunction timing geometric coincidence, unusual morphology standard cometary evolution, emission patterns documented in other comets, brightness fluctuations volatile composition, planetary flybys hyperbolic trajectory geometry. Does that definitively prove natural origin? Number. It proves natural origin is sufficient to explain observations without requiring more complex hypotheses. Occam's razor favours the simpler explanation unless evidence demands otherwise. Loeb's alternative interpretation deserves serious consideration because of his credentials and because science advances by questioning assumptions. His 3,040% probability estimate for possible artificial origin reflects uncertainty, not conclusion. And uncertainty is appropriate when comprehensive data analysis hasn't been published. But most scientists applying the same evidence arrive at much lower probability, perhaps 15%, that 3i Atlas might be artificial. That's not dismissal. That's assessment based on how well natural models fit observations. Here's what changes everything actually means in the context of this title. observational methodology advancement. We proved that coordinated multi-spacecraft observation during interstellar visitor perihelion is achievable. We established protocols that will apply to future visitors. We demonstrated that solar conjunction doesn't mean blind observation. It just means adapting strategy to use spacecraft optimally. When the next interstellar visitor arrives and models predict legacy survey of space and time, LSST, we'll detect 12 per year. Once fully operational, we'll be prepared. We'll know how to position observations. We'll have comparative data from 3i Atlas to benchmark against. We'll have refined models of what typical interstellar comets look like. That's what changed. Not necessarily the object itself, but our capability to study such objects comprehensively. If comprehensive peer-reviewed analysis reveals unexpected features, subtle trajectory anomalies that don't fit outgassing models, spectroscopic signatures inconsistent with natural formation, morphological details incompatible with cometary structure, I'll update my assessment accordingly. That's what following evidence means. You adjust conclusions when new data warrants. But based on what's publicly available now, the verdict so far is 3i Atlas is an unusual but natural comet from interstellar space, providing the most comprehensive perihelion dataset in the history of interstellar visitor studies. Does that mean the story ends? Not at all. December 19th, Earth flyby provides more data. March 16th, Jupiter flyby provides even more. Peer-reviewed papers appearing over coming months will add detail and nuance. Our understanding will continue refining. And there's always the possibility, however unlikely most scientists consider it, that deeper analysis might reveal something we're missing with preliminary observations. That's why we don't close the book prematurely. That's why we keep watching, keep analysing, keep questioning. But we question based on evidence, not wishful thinking. We follow data, not narrative. We remain open to surprises while maintaining standards for what constitutes compelling evidence. That's intellectually honest science. That's the approach that will eventually tell us definitively what 3i Atlas is. And whether it's a comet or something more, the broader implications of its visit matter enormously, which is what I want to close with. Step back from the technical details for a moment and consider what we're actually experiencing in 2025. For the first time in human history, interstellar visitors are routine enough that we've developed protocols for studying them. 3 confirmed interstellar objects in 7 years. Oumuamua in 2017, 2i/Borisov in 2019, 3i Atlas in 2025. That's acceleration in detection rate, and it's about to accelerate further. The Vera C. Rubin Observatory in Chile, operating the legacy survey of space and time, achieves first light later this year. LSST will survey the entire visible sky every few nights, detecting faint moving objects that current surveys miss. Models predict LSST will find 12 interstellar visitors annually, possibly more if they're more common than statistics suggest. Within 5 years, we might know of 10 interstellar visitors. Within a decade, dozens. Our understanding of what's typical versus unusual will improve dramatically with larger sample size. 3i Atlas, regardless of what it ultimately proves to be, represents a milestone in that progression. It's the first interstellar visitor for which we achieved comprehensive multi-spacecraft perihelion observations. The playbook we developed, which platforms to use, which observations to prioritize, how to coordinate international collaboration becomes the template for future visitors. That matters enormously. Because as detection rate increases, we can't treat every interstellar visitor as unprecedented anomaly. We need baseline understanding. We need comparative framework. We need to know what normal looks like so we can identify genuinely anomalous objects when they appear. If most interstellar visitors look like 3i Atlas and 2i/Borisov cometary composition, natural outgassing, gravitational trajectories, then we learn that interstellar space is full of icy planetesimals ejected from forming planetary systems and wandering the galaxy for billions of years. That tells us planetary system formation is violent, with significant fraction of material getting ejected rather than accreted into planets. If some interstellar visitors look different, like Oumuamua with its unusual characteristics, we learn that diverse object types exist in interstellar space, possibly including exotic natural phenomena we haven't yet understood, or, less likely, artificial constructs. Sample size transforms anomaly hunting from speculation into statistics. With 3 objects, every unusual feature seems potentially significant. With 50 objects, you can calculate what fractions show specific characteristics and determine what's rare versus common. This is why I'm fundamentally optimistic about resolving questions surrounding interstellar visitors. We're not stuck with 3 data points forever. We're entering an era of routine interstellar visitor detection. Time and observation will provide answers. There's also something philosophically profound about living in this particular moment of human history. For 99.9% of human existence, interstellar visitors pass through our solar system undetected. We didn't have telescopes. We didn't have mathematics to recognize hyperbolic trajectories. We didn't even know other stars were suns with their own potential planetary systems. The first confirmed interstellar visitor was detected less than 10 years ago. You and I are alive during the transition from we've never detected one to we routinely find them. That's a phase transition in human knowledge as significant as the first exoplanet discovery or the first gravitational wave detection. We live in an era when the universe is less remote than previous generations imagined, when material from other stellar systems passes through our neighborhood regularly enough to study, when the space between stars is an absolute void but populated with wanderers carrying information about distant stellar nurseries. That's extraordinary alien technology or not. Whether 3i Atlas turns out to be a comet or something more, its visit has value. It pushes our observation capabilities. It tests our theories. It expands our understanding of what exists in the cosmos beyond our immediate stellar neighborhood. And here's what I want you to take away from this entire analysis. Stay curious. Keep asking questions. Don't accept preliminary conclusions as final, but also don't mistake speculation for evidence. Stay critical. Apply the same skepticism to alternative narratives as you do to official narratives. Demand evidence from all sources. Don't believe something just because it's exciting or because authorities deny it. Stay engaged. Follow the scientific literature as papers publish. Track 3. I, Atlas, through its December Earth flyby, and March Jupiter encounter. Participate in amateur observation if you have capability. Science isn't something that happens in distant ivory towers, it's something you can engage with. The story continues. Comprehensive papers will appear over coming months, adding detail and nuance. The December and March flybys will provide additional data. Future interstellar visitors will give us comparative context. And perhaps we'll look back on 3i Atlas as the object that taught us how to properly study interstellar visitors, making us ready for the moment when we encounter one that's genuinely, undeniably extraordinary. Until then, we watch, we analyze, we remain open to wonder while grounded in evidence. We acknowledge that not knowing yet is better than claiming to know prematurely, because science isn't about having all the answers immediately. It's about asking the right questions and patiently, rigorously, following evidence toward truth wherever that truth leads. 3i Atlas passed through Perihelion yesterday. The data is being analysed, the papers are being written, the next chapters are approaching. And you now understand why October 29th, 2025 matters not because something sensational definitely happened, but because comprehensive observation of that moment represents the best we've ever done at studying an interstellar visitor when it mattered most. That's worth paying attention to. That's worth understanding deeply. Because we're living through the era when humanity transitioned from wondering about visitors from beyond our solar system to routinely studying them with sophisticated instruments and systematic methodology. The universe is revealing its secrets, one interstellar visitor at a time, and we're here, together, watching it happen. Stay curious, stay critical, stay tuned. Because the story of 3i Atlas and of all the interstellar visitors yet to come is just beginning.